Dr. R. Hemavati is an assistant professor in mathematics in Queen Mary's, Chennai. She has specialized on functional analysis. Having 12 years of experience in teaching, she has won various awards for her performance. She has published papers in 14 international journals, 3 national journals, and has presented papers in 10 international and in 5 national conferences. She is also one of the editors for an international journal.
Welcome to UGC lecture series. Now we are in session 12. In earlier sessions we have seen the discrete and continuous random variables elaborately, finding mean and variance, and we have also dealt with moments and moment generating function, definition, properties, and we have done a problem on moment generating function for discrete random variable. In this session we are going to see the moment generating function obtaining for continuous random variable. Also some problems have been dealt with the relationship between moments and moment generating function. Some concept of characteristic function has been dealt. So, we shall deal with the relationship between moments and moment generating function. Finding the MGF of a continuous random variable is also done. Also the concept of characteristic function, which is new and related to moment generating function, is dealt with briefly. So, the example here is for the finding the moment generating function for a continuous random variable. How do you say it is continuous? Because x is taking the values in an interval. X is greater than 0 means x is taking the values from 0 to infinity, all possible values from 0 to infinity. So, the illustration goes as the number of hours of a satisfactory operations that a certain brand of TV set will give. That is, the life, a satisfactory life of a TV set is being described as a continuous random variable, and its PDF is given by f of x is equal to 500 into e power minus 500 x for x greater than 0, that is from 0 to infinity, and is equal to 0 when x is less than 0. Find the MGF of x, mean and variance. Mean and variance of x we have to find out using MGF. How to do this problem? You are given f of x equal to 500 into e power minus 500 x for x is greater than 0. It is 0 elsewhere. So, we will go with the definition of moment generating function, which is equal to expectation of e power t x. This is equal to integral minus infinity to infinity e power t x into f of x dx. F of x is defined only for x greater than 0. So, they break the interval as minus infinity to 0, this e power t x f of x dx plus 0 to infinity. In minus infinity to 0, it is totally f of x is 0 plus 0 to infinity e power t x into 500 e power minus 500 x dx. We have to integrate this. How to integrate? Is equal to integral 0 to infinity. I shall make the integration compatible for this, which is equal to 500 into integral 0 to infinity e power minus 500 minus t x dx. So, here 500 minus t should be positive. For that we should have 500 minus t is greater than 0, or else t should be less than 500. Okay. Otherwise, the integration becomes divergent and we cannot have moment generating function. So, the integration goes as 500 into e power minus 500 minus t x by minus 500 minus t. Within the limits x is equal to 0 to x is equal to infinity. This is equal to 500 minus 500 by minus 500 minus t into e power minus infinity minus e power 0. This is equal to 500 by minus 500 minus t by e power minus infinity is 0, e power 1 is e power 0 is 1, and we have the integration as 500 by 500 minus t. This is your mx of t. Okay. We have to find out a mean. Mean is equal to mu 1 dash. Mu 1 dash is d by dt of mx of t at t is equal to 0. So, it is d by dt of 500 by 500 minus t. This is at t is equal to 0. Integrate this 500 into minus 1 by 500 minus t whole square. This is within the limits t is equal to 0 into minus 1 because of the differentiation of this 500 minus t. So, this is minus 500 by 1 by 500 by 500 minus t 500 minus 0 whole square, and the answer is 1 by 500. This is your mean. Then we have to find out mu 2 dash. Mu 2 dash is d square by dt square of mx of t at t is equal to 0. What is your one time differentiation? One time differentiation is 500 divided by 500 minus t whole square. This again we have to differentiate. So, one time differentiation we are having 500 by 500 minus t whole square. This you have to put t is equal to 0 after one more time differentiation. So, take 500 outside, minus 2 into minus 1 because of the 500 minus t whole square differentiation, 500 minus t whole cube within the limits t is equal to 0. This is 2 divided by, when you put t is equal to 0, 2 divided by 500 whole square. Let us not simplify this, we shall have it as it is, so that it will be easy for you to find out variance. This is your mu 2 dash. So, what is variance? Variance equal to mu 2. Mu 2 is mu 2 dash minus mu 1 dash square. Mu 2 dash just now we have found out, this is 2 by 500 square minus mu 1 dash is 1 by 500, according to this is square. So, I already told you do not expand this 500 square, so that when you take the simplification, 2 by 500 whole square minus 1 by 500 whole square is 1 by 500 square. This is the variance. We have found out the moment generating function for f of x, for x whose PDF is given by 500 into e power minus 500 x. The next illustration is also important because this particular PDF has in terms of modulus. Okay. Show that if a random variable x has the density function f of x is equal to 1 by 2 e power minus mod x for minus infinity less than x less than infinity, then the MGF is given by, you have to get this answer, mx of t is equal to 1 by 1 minus t square. Let us see, f of x is equal to 1 by 2 e power minus mod x. You are given f of x is equal to 1 by 2 e power minus mod x for minus infinity less than x less than infinity. We have to find out moment generating function, mx of t is equal to expectation of e power tx equal to integral minus infinity to infinity e power tx into f of x dx. But f of x is a modulus function, and modulus function has two definitions, for one for positive, another one for negative. Therefore, it is 1 by 2 e power minus mod x dx, where we know the definition of mod x equal to minus x if x is less than 0 and equal to x if x is positive. So, accordingly we have continuing the integration, mx of t is equal to, break the integral as minus infinity to 0 e power tx e power 1 by 2, I will take it outside already, e power minus mod x dx plus integral 0 to infinity e power tx e power minus mod x dx equal to 1 by 2 integral minus infinity to 0 e power t x e power minus of minus x dx. This is because x is negative here, and integral 0 to infinity e power t x e power minus x dx. So, how this is written so that it is suitable for integration? 1 by 2 minus infinity to 0 e power t plus 1 into x dx plus the previously you are having t minus 1. I am going to write it as minus of 1 minus t, integral 0 to infinity e power minus of 1 minus t dx dx. So, that when you integrate and you substitute the limit to infinity, it becomes e power minus infinity. So, here we should have this 1 minus t particularly as a positive quantity, that is this 1 minus t should be greater than 0 or you should have t is less than 1. Okay. So, what happens to the integration? 1 by 2 e power t plus 1 into x by t plus 1 plus this is sorry within the limits minus infinity to 0 plus e power minus of 1 minus t into x by minus of 1 minus t within the limits 0 to infinity. So, we shall substitute the limits which is equal to 1 by 2, what is that, e power 0 minus e power minus infinity by t plus 1 plus e power minus infinity minus e power 0 by minus of 1 minus t. Okay. So, what happens? 1 by 2, it is 1 by t plus 1 plus 1 by 1 minus t. It is 1 by 2, 1 minus t plus t plus 1, t gets cancelled and it is written as 1 plus t into 1 minus t, a plus b into a minus b is a minus b square, a square minus b square. So, 1 minus t square, t gets cancelled, you have 2 by 2 into 1 minus t square which is equal to 1 by 1 minus t square. Hence, you have proved mx of t is equal to 1 by 1 minus t square. Let us have a break. Welcome after the break. Before the break, we have done two problems on moment generating function for continuous random variable, and next we are going to see some illustration where the moment generating function will be given and you will be asked to find out the mean or standard deviation or the variance. This is what is we are using here, the relationship between moments and moment generating function. What is given? If a random variable x has the MGF, mx of t is equal to 2 divided by 2 minus t, find the standard deviation of x. So, we have to relate the moment generating function with the standard deviation. How is it possible? First of all, we have to find out the variance, then only we can find out standard deviation. For finding variance mu 2, we have to use mu 2 dash and mu 1 dash square. Hence, we have to find out mean, mu 1 dash and mu 2 dash, find variance, then standard deviation using the MGF. Given mx of t is equal to 2 by 2 minus t. So, to find SD, to find the standard deviation of x, first we have to use variance, because standard deviation is equal to root of variance, that is root of mu 2, which is root of mu 2 dash minus mu 1 dash square, where we have to find out first mu 1 dash. Mu 1 dash is d by dt of mx of t at t is equal to 0, which is d by dt of 2 by 2 minus t at t is equal to 0. As usual, differentiation, you differentiate and then put t is equal to 0, you get the answer as 1 by 2. This is mu 1 dash. Then mu 2 dash is d square by dt square 2 by 2 minus t at t is equal to 0. Again 2 time differentiation you have to do and finish off, the answer will be equal to 2 by 2 square, which is 1 by 2. Okay. So, variance is equal to mu 2 is mu 2 dash minus mu 1 dash square. I shall have it as 2 by 2 square minus 1 by 2 square, which is equal to 1 by 4. This is variance. Then what is your standard deviation? Standard deviation is root of variance, which is equal to root of 1 by 4 equal to 1 by 2. This is standard deviation. Hence, we have found out the standard deviation when its MGF is given. Next problem is when you are given the moment generating function, how to find out the general raw moment about origin mu r dash. Okay. Find the moment generating function of a random variable whose moments are given by. Here moments are given and we have to find out the moment generating function. Okay, it is reverse. So far we have got moment generating function and we have found out the moments. Here we have to find out moment generating function, moments are given. Okay, we have to use the general formula. What is the general formula says? We already know that mx of t is equal to 1 plus t by 1 factorial into mu 1 dash plus t square by 2 factorial into mu 2 dash plus etc. The rth term is t power r by r factorial into mu r dash plus etc. up to infinity. So, in general it is written as r is equal to 0 to infinity t power r by r factorial mu r dash. Okay. So, now we have to substitute for mu r dash, which is given in the question as r plus 1 factorial into 2 power r. What is the relationship between r plus 1 factorial and r factorial is, we can write t power r by r factorial. We can write r plus 1 factorial as r plus 1 into r factorial, okay, into this 2 power is already there. So, r factorial gets cancelled. I will combine this 2 power r and t power r as 2t power r. We can write 2t power r into r plus 1. Okay. Now, expand this. First put r is equal to 0, you get 1, then put r is equal to 1, you get 2 into 2t, then you put r is equal to 2, 3 into 2t whole square plus etc. up to infinity. This looks like the series 1 plus 2x plus 3x square plus etc. up to infinity. What does this summation stands for? It is 1 minus x whole power minus 2, okay, where x is equal to 2t. So, we have 1 minus 2t whole power minus 2. This is 1 by 1 minus 2t whole square. So, this is the moment generating function required when the moments are given as r plus 1 factorial into 2 power r. Next, so far we have dealt with moments and moment generating function. Shortly we will discuss the characteristic function, which is closely associated with the moment generating function. Now, I would like to stress what is the moment generating function definition we have already seen. Mx of t is equal to expectation of e power tx. Here the characteristic function definition goes like x be a random variable, the function pi x of t called the characteristic function of x is defined by, just recall, compare with the moment generating function definition. Pi x of t is equal to expectation of e power I tx. There this I won't be there. What is this I? This I is nothing but an imaginary number root of minus 1. Okay. So, when x is discrete, we will have a summation e power I tx into p of x, and again pi x of t is equal to expectation of e power I tx equals to integration e power I tx into f of x dx when x is continuous. The integration taking all the values from minus infinity to plus infinity. Only difference between characteristic function and moment generating function is the imaginary number accompanying the power in the exponential. So, what is the property? We shall see some properties of characteristic function. Pi x of 0 is equal to 1. What is this pi x of t? There you put t is equal to 0 and you will get 1. How to prove this? We know that pi x of t is equal to expectation of e power I t x. So, what is pi x of 0 going to be? Pi x of 0 is equal to expectation of e power I into, in the place of t you are having expectation of e power 0 is equal to 1. Hence proved pi x of 0 is equal to 1. The next property is modulus of pi x of t is less than or equal to 1. Okay. These kind of properties we have not seen in moment generating function, since here the I is accompanying with the power of exponential, we can have all these properties. So, how to prove this? Property 2, take the left hand side, which is modulus of pi x of t. According to the definition, this is modulus of expectation of e power I t x, which is less than or equal to, when you take the modulus inside, you should have the less than or equal to, and modulus of e power I t x is e power I t x is cos t x plus I sin t x. So, modulus of e power I t x will be equal to root of cos square t x plus sin square t x, which is equal to 1, root 1 which is 1. Therefore, your left hand side remains as expectation of modulus of less than or equal to e power expectation of I t x, which is equal to expectation of 1, right, which is equal to 1. Therefore, we have pi x of t modulus is less than or equal to 1. In this session, we have seen the moment generating function finding for continuous random variable. Also, a problem has been done when the moment generating function is given and you will be asked to find out moments, and when moments are given you will be asked to find out the moment generating function. Also, characteristic function definition has been established and some properties of characteristic function has been discussed. Based on one of the example we have done for continuous random variable whose MGF has to be found out, we can do this problem. Find the MGF of continuous random variable whose PDF is given by f of x is equal to 1 by 2a e power minus modulus of x minus a by a. It is similar to the second problem we have done for minus infinity less than x less than infinity. Carefully take the modulus for x is greater than a and one interval and another interval x is less than a. So, you have to break the interval minus infinity to infinity at a as minus infinity to plus a and a to infinity, and using MGF as usual we can find out mean and variance. So, in this session we have dealt with the relationship between moments and moment generating function. Also some properties and definition of characteristic function is dealt. Thank you.